Okay, this problem says a commuter backs her car out of her garage with an acceleration of 1.4 meters per second square. How long does it take her to reach a speed of 2 meters per second? So when you're in the garage, you start off at rest. Okay. So let's say you're at the garage and that's the direction, and you accelerate in this direction. Okay, so the acceleration is 1.4 meters per second square. If the acceleration was pointing in that direction with this axis, it would be negative 1.4 meters per second square. Okay. And then you want a final velocity of 2 meters per second. Okay, you saw that you have this equation. Velocity as a function of time is given by that. V naught is the initial velocity, acceleration times time. Okay, so in our case the velocity was 0, so V equal to AT. T is the final velocity divided by the acceleration. 2 meters per second, 1.4 meters per second square. Your left meters per second cancels, you're left with a second, which goes on top there. So she reaches that velocity at 1.43 seconds. And part B, so she's going at 2 meters per second. If she then brakes to a stop in 0.8 seconds. So you'd see, to speed up to that speed, it took 1.43 seconds. And now you're going to stop in 0.8 seconds. Okay, so you're going to stop. So you're going to stop in a smaller time, so your acceleration has to be greater. Okay. So again, we'll use the same equation, V equal to V naught plus AT. Okay, so this time what is happening? You were going at 2 meters per second, and what are you doing? You're stopping. All right, so let's see, what is your final velocity? 0 meters per second. What is your initial velocity? 2 meters per second. Okay, and you're stopping 0.8 seconds, so we'll calculate the acceleration. And I'm not putting units here because it gets messy. So A is negative 2 divided by 0.8, which is negative 2.5. Okay. What does the negative sign tell you?
Well, you're accelerating in the opposite direction.
Yeah, so now your acceleration is in that direction. Yep. Notice when you were accelerating, the magnitude of the acceleration was 1.4 meters per second. When you're braking, the acceleration is much larger. And this is a safety feature, and this happens in all your vehicles and stuff like that.
So I'm just wondering for the velocity function.
This one?
Into the zero. Yeah, yeah. Is it just a normal velocity function like the one we did earlier?
Yeah, this is exactly the same equation. That's the velocity. So again,
So like what would be like the original that you're getting that one from?
so if the velocity is linear, the original function is a quadratic function. Okay. And so if you want, I mean, so you could use this equation. The other equation is x equal to x naught plus v naught t plus 1/2 at squared. That's the function you're getting it from. All right, so again, see, so this is a general feature. Okay. Your braking accelerations normally are always greater than your acceleration when you're speeding up. I guess the only time that's not true is in a boat, because you have the same number of jets. Okay. A particle has constant acceleration of 6 meters per second square. If its initial velocity is 2 meters per second, at what time is its displacement 5 meters? So they're asking for the displacement, and here's an equation for the displacement. That's initial velocity plus 1/2. Okay. So 2 meters per second. Oops. So again, I'm going to not write units because it'll get messy. Plus 1/2 6t squared. So now this is a quadratic equation for time, and you have to solve that. Okay. So this is 5 equal to 2t plus 3t squared. And of course, a quadratic equation has 2 roots. That's 4, 20, 60, 64. All right, so okay, so after 1 second, it'll have a displacement of 5 meters. It'll have traveled 5 meters. Okay, now generally, so that's the solution you want. Okay, generally the other solution has a good interpretation as well. Sometimes it's hard to interpret it. Okay, so what we have is, for this quadratic equation, that is 5. And for the negative solution, see, if this velocity was negative, initial velocity was negative 2 meters per second. It was negative 2 meters per second 1.67 seconds ago. Okay, so what this is so you can think of this as 1.6 seconds ago, 7 seconds ago, if this was negative and the acceleration is 6 meters per second square, the acceleration is in this direction, it slows down and then eventually comes back. Okay, and that'll be 5 meters. So again, right now, that's the solution we want. Again, but if you think about it, those other solutions have interpretations as well. Okay. All right, this is a problem similar to what we've done, so you guys can look at it. Okay, so here's an interesting problem. A woodpecker's brain is specially protected from large accelerations by tendon-like attachments inside the skull. Okay. So, so let's say here's the skull. Um, all right, I'll draw. So this is the brain, and these are sort of rubber band attachments to the skull. And the idea is as follows. Okay, so in all safety devices, here's the issue. You guys know Newton's second law. The greater the acceleration you experience, the greater the forces acting on you. Okay, and that's what causes damage. Okay, so a lot of safety devices in your life, like airbag and stuff like that, what they are about is they're to reduce the acceleration. Okay, so here's an example I like to give you. So let's say you jump off the top of this building and the sidewalk stops you. That'll hurt. On the other hand, if you jump off the building and let's say you jump off on a mattress or something, you jumped off from the same height. Why didn't that hurt as much?
Because the mattress cushioned you from...
So you stopped over a larger distance, and here's the equation. Okay, v square is v naught square plus 2ax minus x naught. Okay, so you stopped, that was your initial velocity. Okay, all that is the same. If you stop over a larger distance, if this is larger, the acceleration is smaller. Okay, so that's a common theme in a lot of your safety devices. Okay, you want to reduce the accelerations the person experiences. Okay? And you guys know that football players' concussion is a issue. Okay? So let's say I'm going to draw a prehistoric woodpecker. All right, so here's the skull of a prehistoric woodpecker. By the way, so here's a prehistoric woodpecker. And you know, the woodpecker is pecking on the tree and it pecks on the tree millions of times a second. Okay, let's say it's going at, I'm just making up these numbers. Okay, well, here it is. 1 meters per second. It pecks on the wood and then it stops. Okay, it goes from 1 meter a second to 0 meters a second. Okay, so the skull stopped when the beak hit the thing. What was the velocity of the brain? 1 meters per second. And then the brain runs into the skull stops it. Okay, and it's soft tissue, so it just stops it, and it stops it over a small distance, and the brain gets crushed. You do it 1,000,000 times a day, you're going to damage the brain. So how did nature solve this problem? Eventually this evolved. These rubber bands, Well, how does this solve the problem? Okay, now let's set it, get this woodpecker to peck on that tree. The skull stops, and this brain is trying to go hit the skull, except that these pull back and on it and slow down the thing. So this brain is stopping over this distance, okay, over a larger distance, and so, and hopefully it doesn't hit the skull. Probably doesn't hit the skull. So all these tendons are pulling back, decreasing the acceleration. Yep. So anyway, that's what the problem is about. Okay. So it's a good solution nature has come up with. Okay, so a woodpecker's brain is specially protected from large accelerations. Okay, again, large accelerations are bad. By tendon-like attachments inside the skull. While pecking on a tree, the woodpecker's head comes to stop from an initial velocity of 0.6 meters per second in a distance of only 2 millimeters. Okay. So the skull is decelerating over 2 millimeters. Okay. Find the acceleration in meters per second square in multiples of g. Okay. Okay. So again, this is the equation you use. Okay. So in that diagram, that's x, that's the x-axis. The initial velocity v naught is in that direction, okay, which is 0.6 meters, and the final velocity is 0. So the acceleration is v square minus v naught square. Okay, the final velocity is 0. The initial velocity is 0.6 meters per second square. And it's coming to rest. Okay, there's final x, this is initial x. So it's 2 millimeters. And a millimeter is 10 minus 3 meters. Okay, so that's negative 0.36 over 4 into 10 to the 3 meters per second squared. Okay. And that's 360 over 490. Okay. So minus 90 meters per second squared. All right, now pay close attention to this. That's the acceleration. Okay. What does the negative sign tell you? The negative sign tells you if that's positive, the acceleration is pointing in that direction. Okay. You're slowing down. Okay. Is this a large acceleration? Okay, so to get a sense for this, this is what we'll do on a regular basis. So this is to get a better sense of this. There's 90 meters per second square. G divided by 9.8 meters per second square. What is this guy? That's 1. That's G divided by that magnitude. That's 1. Okay? I'm going to multiply it by that. You'll see in a second why I'm doing this. Well, 90 divided by 10 is roughly 9. Okay? Okay, so that's 9.2. So the acceleration was 9.2 g. Okay, why did I write that? Okay, what's your weight? Your weight is mg. Okay, so the weight of the woodpecker's head is the mass of the head times g. So the stopping acceleration, the force that the tree exerted on the head to stop it, is 10 times the weight of the head. That's what that means. And now that gives you a better perspective. All right, do I want to stand here and hit my head on the wall with a force 10 times the weight of my head? 100 million times a day? No. All right, let's see what the tendons will do. Okay. Calculate the stopping time. Okay, we won't worry about that. The tendons, you go talk to Abdu about that. Okay. The tendons cradle the brain, stretch, cradling the brain stretch, making the stopping distance 4.5 millimeters. Okay, now, so here's the acceleration. You increase the stopping distance from 2 millimeters to 4.5 millimeters, more than twice that. And so the acceleration will be half of that. That'll be less than 4 Gs. Okay, and so that's what you're doing. So part C, acceleration is v square minus v naught square. And that will work out too. Okay, so instead of 9 times the weight of your head, now the stopping force is 4 times the weight of your head. Okay. So again, the idea is you want to high G's are damaging. Okay. Okay, I'm going to solve one more problem. And okay, I'll solve this one. So this is a bit involved, and then please go to the SI session. It's a very useful free service. Okay? Abdul is not supposed to charge you anything. So you throw a ball straight up with an initial velocity of 15 meters per second. It passes a tree branch on the way up at a height of 7 meters. So you're going to throw the ball up from there at 15 meters per second. Our axis is pointing that way. Acceleration is, what is acceleration? In
9.8 meters per second squared.
on this axis, it's the y component is minus g equal to minus 9.8 meters per second squared. Okay. All right, this velocity is positive. Okay. It passes a tree branch on the way up at a height of 7 meters, so this is 7 meters. How much additional time elapses before the ball passes the tree branch on the way back? Okay, so what happens is the ball is going up like that and then falls back like this. Okay. So what we want is the time spent above the tree branch. Now, I haven't proved this to you guys, but you guys understand this. I mean, it's sort of intuitive. If you throw a ball up, the time it takes to reach its maximum height is the same time it takes to fall down. You guys understand that? So this time will equal that time. Okay. All right. Maybe we might use that. Let's see. All right, so let's do part one of the problem. Let's find out how long does it take to get to 7 meters. Okay. All right, what is its velocity at that time? Yeah. So we'll call this V. Okay, so V square is V naught square is initial velocity is that 2 times negative 9.8 and and this is 7 meters. So there's the x naught, V naught is that, acceleration is negative 9.8 meters per second squared. Okay, so when it gets to the tree branch, it is going at all right, so it's going at 9.37 meters per second. All right, so part B, now it's going at 9.37 meters per second. Okay, so you need to assume, well, I haven't proved this. The time taken to go up is equal to the time taken to come down. At the top, it's going at zero, its velocity is 0 because it doesn't have an x component. Anyway, or we could do the following. When it comes back to the bottom, its velocity is negative 9.37 meters per second. When you come to the same level, you're going at the same speed. All right, so we'll use this and calculate the time it spent above the tree line, above the branch line. Minus 9.37 equal to 9.37 minus 9.8 t. And that will be in seconds. Okay, you guys understand that? So now it spent 1.91 seconds above the branch. All right, let's do this one problem as well. Oh no, let's do this one, the hot air balloon. Okay, so a hot air balloon rises from ground level at a constant velocity of 3 meters per second. 1 minute after liftoff, a sandbag is dropped accidentally. All right, so here's ground level. It's going at 3 meters per second. And 1 minute later, 1 minute is 60 seconds. So it's still going at 3 meters per second. that's 180 meters. Okay, then you drop a sandbag. When you drop the sandbag, what is the velocity of the sandbag?
Initially 0, or sorry, 3 meters per second.
Very good.
Yeah.
Okay, so you drive on 95 at 80 miles an hour, you drop an orange out your window, it's going at 80 miles an hour. Okay, and then it starts falling. So its initial velocity is 3 meters per second. And then it'll rise up and then fall down. Okay. The time it takes for the sandbag to reach the ground. Okay. And the acceleration is negative 9.8 meters per second square. We're assuming, okay. So x minus x naught equal to v naught t plus 1/2 at squared. Final x position is 0. Initial x position is 180 meters. So 0 minus 180, 3t plus 1/2 negative 9.8 t squared. So we'll solve this quadratic equation. You good? Okay. So the sandbag hits the ground 6.4 seconds later. Okay. What this solution, the negative solution, is telling you is the following. Had you thrown the sandbag from the ground at a velocity such that it would have had 3 meters per second there, velocity there, it would have been on the ground. If this is time t equal to 0, it would have been on the ground 5.77 seconds ago, or negative 5. Okay. That's what that negative solution means. But again, like I said, a lot of times this is a little messy, a little subtle to interpret. You don't have to worry about it. I'm just mentioning it because, down the road you can give meaning to.
So if it is on the ground.
All right, so here's the sandbag, here's the velocity. Okay, so think of this. I'm going to throw this. Okay, we looked at this motion. Okay, so if this sandbag you could have thrown it from the ground level, it could have gone. Okay,
So from the ground, 3.
so no, from the ground you would have to throw it at the appropriate velocity. I don't know what the velocity is. I can calculate the final velocity and tell you.
Okay. So it's from the ground, it would be
Yeah.
negative 5.
So if that was 0 seconds, that would have been minus 5.77 seconds.
Okay.
That's what that means. All right, guys. So